Okay, let's start. Do you have any questions? All right. So, as mentioned, we're gonna talk about 5.1 today and move to 8.1 and then 8.2 to round off the material for this semester. So, (5.1), okay. So chapter 5, right, is about nonlinear system. And 5.1 is equilibrium point analysis. All right. So, and this is the only section that we will deal with in this chapter. So, the point, right, is to discuss the. So let's look at one example, right? Let's say x prime is minus 2x plus 2x squared. Y prime is minus 3x plus y plus 3x squared, right? This is one example. Well, we can look at another one. So this is the text lecture. Another one would be something like, let's see, right? X prime is x times minus x minus 3y plus 150. And then y prime is y minus 2x minus y plus 100, right? So this is problem 7. So, right, what do we want to do here? Okay, so first of all, right, the very obvious thing is to recognize, right, these are nonlinear systems, right? So we don't have, like, generically, we don't have explicit solutions for the system, right? And so no explicit solution. Okay, so where does the nonlinearity come from? For example, in the first example, it comes from these two terms, right? 2x squared and 3x squared. In the second one, right, it basically comes from multiplying, right? So all the terms here are nonlinear. Okay, so I mean, I guess the last one, right, is a linear term, but these cross terms, right, will all be nonlinear. Anyway, right, so I hope it's obvious that you recognize, right, that where the nonlinearity comes from. But overall, it's just basically the systems are nonlinear. So whatever techniques we learned from chapter 3, right, does not apply directly. So in 5.1, right, what are the goals? So the goal is, first of all, identify, right, all equilibrium points as before. And goal number 2, right, is to classify this equilibrium. Okay, maybe let me say this, right? This really is goal number 3, but so maybe let me say this is goal number 3, finding the linearized system around the equilibrium point. Okay, so the theme, right, of the 5.1 section is to find a linearized system. Or actually, if I have to guess, the theme of the book in general, right? Sorry, the book, the chapter 5 in general is about the linearized system. In other words, right, we cannot solve the nonlinear system directly. So we find some approximate, okay, linear system around certain points, because usually that's the point of interest. And then you kind of proceed and analyze the system at that point. So that's a theme. Again, right, we don't have time to go through the whole chapter 5. So the only kind of thing that the analysis we do is the qualitative analysis, right, of studying the nature of the equilibrium solution around that point. Okay, so we have discussed how to do one, right? One generically is just basically set, right, the right-hand side equal to 0 and find all the points that make them equal to 0, right? So for example, right, so in goal number 1, you're looking at the system, right, x prime equals to minus 2x plus 2x squared, y prime is minus 3x plus y plus 3x squared. So, right, you set both of them to equal to 0. So minus 2x plus 2x squared is equal to 0, and then this equal to 0, right? And you solve for it. So let's see, right? I mean, and there's no real systematic way to do this besides, right, look at the first equation, try to see what you can do by factorization, and look at the second equation and see what you can do, right, with the factorization. So the top says, let me see here, right, minus 2x, and then you got minus 1, right, plus x, right, is equal to 0. Okay, sorry, 1, right, 1 minus x. So, and then the second one, let's leave it the same, right? So the top says x equal to 0 or x equals to 1, right? And if x is equal to 0, if you plug in the second one, you see that y equals 0. And then for the second one, if x equals to 1, y is also equal to 0. Right, so these are two equilibrium solutions that the system have, okay? So that's number 1, right, pre-standard. We looked at this before. Number 3, right, of course, relies on number 2. So we want to discuss the idea of linearization, right, of the system. What do we mean, right? So step 2, finding the linearized system. Okay. So questions so far before we proceed to step 2? Okay, so let me kind of, right, instead of, we'll go back to the example, but in the abstract, right, is something like this. So let's just consider, right, the system x prime equals to, let's say, big F, okay, and y prime equals to g of xy, okay? And let's say we want to look at this around the point x naught, y naught, okay? So what's so special, right? This is an equilibrium solution. So x naught, y naught satisfies that right, when you plug x naught, y naught into this, they both are E0 because that's equilibrium solutions, okay? So I want to, right, so basically the idea actually is a calculus idea. Idea is linearized, okay, fxy, gxy around this point. And to be frank, it's basically approximation by a tangent line is the idea, okay? So let me go back to the one-dimensional case and remind you of what that is. Suppose you have a function like this, let's say, all right? And this is the point x0. This is f of x, right? One dimension. Then, right, the whole point is the tangent line, right, is a pretty okay approximation of this function around x0, okay? So what's the tangent line, right? The tangent line here is y minus y naught, right, which is f of x naught, is equal to, or let me do this, right, maybe f prime of x naught times x minus x naught, right? This is the equation for the tangent line, right? Or the tangent line has the following formula. Okay, it does a pretty okay job, right, of approximating the function around x naught. Okay, that's the whole writing out of this picture. Of course, right, I mean, this is not the only approximation. You can do second order, third order, whatever, as long as, you know, this function is smooth and has more derivatives. But what's important for us, right, is this is a linear, right, function, right? This is a linear function, okay? And linear stuff is good for us because we know how to solve linear differential equations. But okay, so this is, right, this is exactly approximation by tangent line in one dimension. And so we will repeat the idea, right, with f and g in two dimension, okay? Any question? And so in two dimension, right, the version should be like this, right? fxy is approximately f of x naught y naught plus partial, right? Or let me do f sub x, right? At this point times x minus x naught plus f sub y at this point times y minus y naught, right? And what do we know? Well, what we know is this guy is 0 because that's the equilibrium solution. So in other words, it's just going to be, right, f sub x okay? So similarly, right, exactly the same argument on the g would give you yes. Any question on this? Okay, so now let's plug this back into our system. What's our system, right? Our system is x prime equals to f of xy, right? Now we specialize around this point only, okay? Emphasis, right? It's like you look at around this, the behavior only around this, okay? Of course, the further you go out, the more imprecise is approximation, but our interest is only locally around this point, so, or around x naught, y naught. And so this is approximately, right? That, and then, so let me do this, right? Y prime is g of xy, right? And let me do one single approximation like this. F sub x, f sub y, g sub x, g sub y, evaluated x naught, y naught, times a vector x minus x naught, y minus y naught. Are we okay? Are we okay? So this is the matrix A, right? This is the matrix A. All right, this is the matrix A. Now, if you're a little bit observant, right, you notice one thing. Well, what's the vector of the changing thing, right? It's going to be x minus x naught and y minus y naught. In the language of physics, right, this is a displacement of x and y away from this equilibrium solution. But on the left-hand side, you have x prime and y prime. Okay? So it's not quite the same, right? Because, you know, you rather have x prime, y prime, right? The whole point is equal to a, right? xy. That's a setup, okay? So the complaint, right? A slight complaint is this and this are not the same variable, or the same function, rather. It's not the same function, right? Not the same function of t. Well, never mind, right? Because this is, the prime here is a lazy way to write the derivative in terms of time, right? And x naught is a constant point. So in other words, d over dt, right, of x of t is clearly equal to d over dt of x minus x naught, right? Same thing for y. Okay, so pay attention, right? Again, there are many things floating around now, and so pay attention. X and y are function of t. X naught, y naught are fixed points, like, you know, 0, 0, or 1, 0. Okay, and when I do this, right, it's also a fixed value matrix because I plugged the value, right, into this function. All right. So when I differentiate, right, a fixed point, I get 0. And that's why this is true. All in all, right, what this suggests is this, that the linearized system is okay, if you denote, let u, right, be x minus x naught, let v be y minus y naught, then the system is u v prime is equal to, and let me call this like this, right, j x naught y naught times uv, the linearized system, right, around this point, where, right, J is the Jacobian matrix. F sub x, F sub y, G sub x, G sub y. Any question? All right. So the only point I want to emphasize, right, is if you read between the line and you're not careful, you may think that the linearized system is the linear version of this old system. That's not true. The linearized system, okay, is the system that talks about the displacement of the original solution away from the equilibrium solution. But that doesn't matter, right? If you know where you are, where you were, and you know your displacement, you should know where you are. So, but right, you got to be careful in terms of meaning because it might mess up your thinking if you don't know what object you're looking at. This is the displacement, okay, not the original position. On the other hand, right, I mean, when you solve for mathematics, whether you call this x, y, or uv doesn't change anything. So if you abuse notation and you call this x, y again, probably I won't raise much of a big deal, except, right, I think rigorously, right, to avoid confusion, you should try to switch to a different notation to remind yourself that you're not talking about the original system, but some displaced version of it. All right. Any question? So looking at the example, right? looking at the example. Then the example we had was x prime is minus 2x plus 2x squared. Y prime is minus 3x plus y plus 3x squared. The equilibrium solution, right, are 0, 0, and 1, 0. Okay? So what's the Jacobian in general? The Jacobian in general would be partial with respect to x, right? So minus 2 plus 4x, 0. Partial with respect to x is minus 3 plus 6x, and then 1. Wow, it's a simple Jacobian as you can get, right? And so the linearized system, right? So A around 0, 0 would be, right, UV prime is minus 2, 0, minus 3, 1 times UV. By the way, right, in the special point of 0, 0, then actually this is the same as xy, right? Because x minus 0 is x. So whether you call it UV or xy doesn't matter here, but let's just use UV to emphasize which switch notation. Around 1, 0 is UV prime is 1, right? So 2, 0, 3, 1. Wow, it just switched like that times UV. Any question? Okay, so that's how you find linearized system around a point in general. Basically, just take the Jacobian. That question does not mean much. Even if the system is linear, our solution is non-linear to begin with. So what do you mean by what if y is non-linear? Oh, okay, I don't know. This is a textbook problem, but let's do something else. I may mess up, I may mess up the solution, but it's just Jacobian. So let's say, suppose, right, that x prime is minus 2x plus 2x squared, y prime is minus 3x plus y squared plus 3x squared, right? Then the top still says, right, x equal to 0 and x equals to 1. And if x is 0, the bottom still says y equal to 0. But if x equals to 1, oh, it's still the same. Huh. Okay, is y squared good enough for you, or you want me to change to something else? So 0, 0 and 1, 0, right, are still, actually this doesn't change anything. Because actually, right, are still equilibrium. I'm not sure this is too cheap. Are still equilibrium, right? And then the Jacobian now will be minus 2 plus 4x, right, and 0. Here will be minus 3 plus 6x, and then 2y. But it won't change anything. I'm giving an example to Albor's question. I'm not doing the same example. But like Albor's, I just happened to land on the same exact thing, but Jacobian, you plug in, right? Notice in the abstract argument, I made no assumption on these guys, besides the fact that they have partial derivatives. Should be continuous and all that jazz, but like nothing about linear, non-linear stuff there. All right, any other question? All right, so now going to step 3, right? Classifications. So do remember, right? When you do classifications, you mean classifications of the original system, all right? Because of course, right? We definitely know how the the behavior, right, of the linearized system is in terms of sink source, circle, whatever, spiral, that kind of thing. Okay. So, but of course, right, the whole idea, right, the whole beauty of calculus, if you will, right? I'm not sure you think that calculus is beautiful or not, but the whole beauty of calculus is that it allows you to say something, right, about some simpler approximation and then carry it back to the original one. Okay, of course, you have to be careful to see if it does carry back to the original one. But right, the whole point is if you simplify stuff, sometimes, right, things just work in the same way as a simplified version and then the original, the more complex version. And that's where calculus helps you out. So, okay, so the simple thing is like this, right? Then the linearized system, right, is the same as the original. In other words, right, if you found this to be sink is sink, source is source, they are the same in all cases except 2, center and 0 eigenvalue. Okay. In other words, right? Okay, so let me say this. So going back to our original example, that you have, right, that x prime is minus 2x plus 2x squared, y prime is minus 3x plus y plus 3x squared. By the way, right, I guess I make a big deal about saying this is nonlinear system, blah, blah, blah. Does this system have explicit solution? Does this have an explicit solution? Yeah, it's partially coupled. If you want to, you can solve it, okay? Yeah, so I think the book just chooses to make it an easy example, but here, this one can be solved explicitly if you want. Anyway, so around 0, 0, right? Around 0, 0, we concluded that it's going to be something like this, right? UV prime is, what was it? Minus 2, 0, minus 3, 1. Right? And clearly, the nature of the 2 eigenvalues are this. So it's really a saddle. So that means the original is saddle. Meaning this. Okay. I mean, I guess if it holds, you don't have to say it. And if it's 0, 1, 0, right, then you got sorry, right? It wasn't that. It's 2 and 3, right? So that's going to be a source. And also holds for the original. And that's it. Any question? Okay, so I'm going to show you the picture of this in the book, right, to point to you what it looks like in terms of putting all these together. But I guess I'm going to search around the books a little bit, so I'm going to stop sharing, and then I will look for the book and I'll share again. All right. All right. So here, right? So you see, this is around 0. It's a saddle point. This is around, so okay, not around 0, right? This is around 0, 0. This is around 1, 0, and it's a source, right? Now, this is just, what is this? You see, this is the complete picture. Meaning this is the original system, all right? Where this is the first equilibrium point, this is the second one, right? And I guess this, right, is obviously a magnification, right? To show you that when you zoom in, you see this and you see that. Okay, so that's what we've been doing so far. What we did not do, and I don't think, right, we have the time to properly address this, is the connection between these two guys when they're close enough to each other. All right, because I think there's something really beautiful here when you put these two together like this. You know, so we found this point, we found this point, right? But these two somehow kind of talk to each other too, because you see, this is a source, it leaves here, but you see how it comes to here. And this actually has a name, it's called a separatrix. So it separates the solution above and solution below in terms of behavior, all right? That's not something I want to get into in the sense that I don't have proper time to give justice, right, to this. But, right, you can see, right, that I think the idea we've covered, right, we discussed up to now is kind of nice, but you know, that's just basically locally, right? Okay, this point linearized, this point linearized, here's how it does, how we do it. But of course, if these 2 points are too far out, I don't know. But when they're kind of close each other, you see then a source and a sink may have interacting, right, between each other, which is super fascinating, right? That again, right, I don't have time or even frankly speaking, the expertise, right, to even give it justice. So, but right, so do pay attention, or you know, to appreciate this further connection, if you will, right? So not only these two disconnected picture, which we talked about, but how they can be put together like this. Okay, but that's the picture. Any question on this? I cannot see the chat. Let me see if I can see it some other way. All right. Any question? I can't see your chat, so maybe let me stop share a little bit. Is that basically the bifurcation of bifurcation? Nah, no, nothing like that. Because bifurcation is the idea that a matrix, right? Your system depends on parameter. Here, there's no dependence on parameter, right? There's no free parameter. There's no free parameter at all. So, whoops. Okay, so there's no free parameter at all. You know, there's no alpha and things like that that runs around in terms of your system. It's basically just uh, right, the system itself being nonlinear. So nonlinear creates several things, right? First, it creates more than one equilibrium solutions. And second, right, these equilibrium solutions, once you have more than one, they could be interacting in some way. I mean, by interacting, maybe it's my own word to say, right? Something leaving from the first one may come to the second one or something like that, right? I don't know. I'm just sensing that there could be some level of interaction between these two equilibrium solutions. Okay. Yeah. All right. So lastly, right, I want to address the idea of the exception. So of course, you can just take this. Basically, this means that nothing can be said. Okay. If you see a center, okay, in your linearized system, unfortunately, you cannot infer back about the original nature of the system, the original system. Does anyone know why that's the case? And also same for zero eigenvalues. Why? So some intuition, right? Why lambda equal to 0 and center are no information case? Why is it that we can say something about source, something about sink, but we cannot say anything about center or zero eigenvalue? By the way, right, it holds a spiral too, okay? Spiral source is spiral source, spiral sink is spiral sink, saddle. Anyone? No, it has nothing to do with the initial condition. By the way, right, initial condition is about this kind of thing. Initial condition is where you start, right? Where you start. So basically, if you start here, then you diverge up. If you start here, you diverge down. So that's the separatrix, right? That's the beauty of the separatrix. If you start here, you go in, you go away, etc., right? The initial conditions where you start on this graph and follow line. What we're referring to is, right, the nature of this point right here, right? And we're saying that if you zoom in, okay, if you zoom in and you see a circle, and that's not true, right? If you zoom in using your linearized system and you draw a circle, right, like this, then when you zoom out and you look at your original system, you cannot say that. Why? Why it's ambiguous? What about the center that makes it ambiguous? So right, actually, it's quite simple. It kind of has to do with the idea, right, that it's because of approximation, okay, and that's again what calculus is about. When we do linearized system, right, linearized system approximate the original one, right? That's the whole idea of doing linearized system, meaning we say, right, that whatever happens to linearized system should hold approximately for the original system. But what does approximation really mean? Approximation, right, at the heart of it, or at least bluntly speaking, means there could be error, right? There not even could, there will be error, right? Small error, right? So let me just say approximation goes with the whole idea of small errors, right? Of course, if you have big error, you shouldn't call it approximation to begin with, right? But when is it a small error preserve nature of things? What do you mean by that? What do you mean correspond to a different solution? No, I don't know if you are talking about the same thing, but reading it word for word, both of you, I don't agree, or I don't see. I'm not seeing the idea. Right? The idea is very simple. What does the center mean? What does the center mean? What must it be for us to have a center in the linearized system? Center means the eigenvalues must be exactly plus minus bi times 0. Not just complex, right? That's the whole point. Not just complex. It must have real part equal to 0. But now, with the small errors, right? The small errors, if it affects the b, does it change the complex nature of the b? Should not. But if it affects the 0, does it still hold that it's 0? That's exactly the point. 0 is very delicate a point, right? You swing one side, you're positive. Exactly. You swing the other side, it's negative. So, I mean, of course, the original system must be a plus or a minus or whatever. You know, the original system must have a nature of it all, of its own, right? But because in the linearized system, you just happen to be right at the borderline. So with the error, you cannot say anything, right? The original system could be center too, right? I mean, cheaply, you linearize a linear system, it's still linear. So if the original linear system is, you know, but right, so 0 is a very delicate point. It can swing either way. But of course, if you have a sink or a source, right? So change 0 to plus minus whatever, you know. Okay. But if you have like let's say a spiral sink, okay, to demonstrate the point. The spiral sink means what? This must be a plus minus bi, where a is negative, right? And again, very close to the point, right? The error is understood to be super small. Then when you move away a little bit, right? The negative, you still have room to move around, right? You still have room to stay negative. And that's why negative sink stays negative, right? And still a spiral sink when you go back to the original one, right? That's why you stay away from 0, as you have room to move with a really small error to stay with the same nature. But 0 definitely does not allow you for that. And that goes for the same explanation as lambda equal to 0. Is that okay? So that's the calculus, right? That's the calculus. Any question? So now, in terms of a practical example, right? The book has a pretty nice example. This one right here. Okay. So this is the system they look at, right? This is the original non-linear system. After they linearized it right around 0, okay, around the center, you get this. And this has a center. Okay, this is a center. While the original system, right, they show using some very easy argument that show that this component, right, is radially pointing inward. So it must be a spiral sink. Okay, it must be a spiral sink. And actually looking at this picture, right, I think, I'm not sure it was Daniel or Albors, right, who said the path is not clear, right? I guess this is what you mean, right? The center must have no error to go back to the center, right? I guess that's how I take on it, right? Geometrically, to have a center means you have to go back exactly on that point. But if you slightly deviate, right, you have a slight error, then you could still, right, the circular nature won't change because of that complex part. But you could circle in slowly, you see, ever so slowly. But it's slowly but surely going in. And that's what deceive, right, the zoom in. See, if you zoom in, you might think it's a center. But really, right, it's a spiral sink. Okay, so it's quite nice. Any question? All right, so as usual, that's all for 5.1. Have a look at these problems. Anything that you think you want me to do an example of in terms of these kind of standard questions? So I think of like questions like 3, right, as a standard question. 4 as a standard question. Don't worry about sketching, right? Because sketching is the same as a linear system. So that's just sketching linear system. So I think I'm more interested in finding, right? By the way, right, I won't give you this. You have to find them, right? Here, I guess they give it to you, but find and classify. So, right, actually maybe 7, for example, right? Part A, exactly is something. No information, no information car. That's all we can say. Yeah. Okay. So if all good, then moving on to 8.1. So I guess we will do, right, like I said, chapter 8, 8.1, 8.2. But chapter 8 in general is, yeah, what's the title, right? Discrete dynamical systems. All right. So maybe let me just give a overview on what I think of, right, as this kind of stuff. So first, right, the discrete here refers to, never mind the dynamical systems, okay? Dynamical systems kind of mean that you take a spin of time on things. You think of things as depending on time. But discrete here means discrete time, okay? So right off the bat, right, no calculus. Because calculus is continuous math, right? So no differential equation, that kind of thing. But of course, right, that doesn't mean you don't have an equation. You have the replacement of difference equation. All right. So, for example, it's really fun like this. Something like, suppose you have this. Let's say, like this. A difference equation version may be something like this. Yn minus 2 plus 2yn minus 1 plus yn is equal to n. Okay, I'll put a question mark here, right? I'm not saying that like this and this have to be exact analogy, but like you could see, right, this is called a second order difference equation, non-homogeneous, right? Of course, you could put a 0 here, for example. So surprisingly, like there are tons of connection between these two. Like you see how people solve this, they look at characteristic solution, that kind of thing, right? Very familiar stuff. Exactly. So that's what I'm going to get to next, right? Is another glorious way to say there's a recursion here, right? But the recursion may be like 2 steps recursion, that kind of stuff, right? But so there are many angles to approach this, right? And of course, in 1.5 lecture left, we don't have time to do justice to this. But one of the questions that would be very interesting to ask is like, explicit solution, right? And we don't do it here, all right? So when I say we solved this, last time it was false advertisement, I apologize. You learned this, I think, in the combinatorics class. 3 something, right? The math department offers a combinatorics class. I think superficially I saw that that class does a difference equation. So they would solve that, right? So not here, but of course, to me, that actually is a very, very interesting part in our itself. When can we solve for explicit solution? Okay. Now, by the way, right? So exactly, right? Like Daniel was talking about, you could have, right, a recursion, right? Naturally, these are recursion. For example, let's say like this, right? So recursion, right? A recurrence relation, right? And so another point of view, which I'm not sure if you care to look at like that, is this is nothing. The yn, right, is nothing but a sequence. Exactly. Talk to your TA, Sagar. Right. So the sequence is exactly like the calculus 2 sequence, right? Because here, basically, but of course, right, a sequence in calculus 2 more or less are given as an explicit formula, right? A discrete time kind of thing that we look at, the equation is not given, right, explicitly, okay? The solution, sorry, right? So the representation is not given explicitly, right? So here, right, representation is not given explicitly, right? But you can think of it as a sequence, okay? It would be, I mean, there is a closed form, which is exactly right here, explicit solution. That's one direction that, like I said, I'm very interested in, right? Except that we don't do it in 8.1, 8.2, right? But yeah, right? And not so naturally it's given a non-closed form if you want, right? Naturally it's given a non-closed form, but that doesn't mean you cannot solve it in closed form and study it, right? But so that's all I'm trying to say. Also, right, by the way, these guys are usually given initial condition too, right? So that's exactly what we call initial condition as well, right? So you also have initial condition, and like so many order initial condition, you see that you need exactly so many initial conditions, right? So anyway, right, we don't have time to go into this, but let me give you one more thing that's kind of fun. Like, for example, I'm not sure if you ever, I mean, you recognize this, right? Suppose something like this. So you know what I'm referring to with this kind of thing? Did I do it right? Hold on. Is it, do I need a square root of y here? So I'm referring to this guy, right? So basically, right, I mean, if I translate right, this is exactly the equation, right? That's given. Okay. So that's the recurrence relation that describes this object. Okay. But of course, right, I mean, this is not that explicit anyway, but this is the representation. Another one, right, since it's kind of fun to talk about this, I think this is the famous one, right? This one, this is the Fibonacci, right? So anyway, etc., etc. The point of 8.1, yeah. So the point of 8.1 and 8.2, right, is at least so one point. One point is this: to study guess this equilibrium solution, right, of this system, right? And the asymptotic nature. And their asymptotic nature. What do I mean by this, right? I mean, basically, as time goes on, what happens? For example, right, is to me, when I was taking like I know math classes undergraduate, it's amazing to me that you can know exactly what this number is, as you could carry it out to all the way into the end. Same, right, as Fibonacci, if you carry it out all the way into the end, I guess here you have to give initial condition, right? I believe they start out both ones, am I right? 1, 1, right? And then 2, and then blah, blah, blah. So anyway, right, here I guess the initial condition is square root of 2 or something. But like, do you know what this sequence converges to? Or what this will eventually go to? No, 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 much smaller than that, I think, not 4. Also higher than that, right? You are both like kind of, I don't know. Not sure. No, no, not E, Daniel. It is a algebraic number. Square root of 2 is wrong because definitely it's higher than square root of 2. 4, I think, is too high because what goes on after that is not that. Okay. Anyway, right? So here, think about it like this, right? Actually, the answer lies right here. If there is a limit, right? Let's look at this. If there is a, by the way, did I do it right? This is this representation, right? I hope. Did I do it right, or without a square root of 2 outside, like that? I'm confused. Let me see. What is the form? So y0, right, is square root of 2. Y1 is square root of 2 plus square root of 2. Y2 is square root of 2 plus square root of 2 plus square root of 2. So 2 plus, oh, so I think just this then, right? Yeah, I think it's just this, right? So I need to decide the right form first. Otherwise, what I talk about is nonsense. This is this form, right? Agree? So if there is a limit, right? Let's say L, then it must satisfy Do you agree? Exactly because of this relation. If this converges to a number and this converges to a number, then of course, this must be true. Right? Oh, yeah, that looks weird, right? So again, did I write this form down correctly? Somehow my mind doesn't work. Is yn plus 1 square root of 2 plus yn? It cannot be 2 because, you know what? It could be 2. Sorry. So whoever said 2, I apologize to that person. I'm so sorry because I did not even pay attention to the square root outside. I think it could be 2. It could be 2, right? Because here it says that L squared, right, is equal to 2 plus L, right? So L solves the equation, right? And so L equals to obviously minus 1, or L equals to 2, but minus 1 is not so the solution, right? Because clearly it's a positive limit, so it's going to be 2. It's going to be 2, right? So yeah, Whoever said not two, and I said it's wrong, I apologize. It seems to be 2. Okay. So I'm not sure if you mean 1, 1, 1, 1, 1 equals to something else, but 0. Okay. At the end. Okay. Right. So yeah, Daniel, right? But that's not what we're looking at. We're looking at, right? Notice what we're looking at is the point of where these keep, how to say this, right? If this converges to a number, right? So in the limit, so then whatever that is, right? It will never reach 2, right? You just put in your calculator. This number, I guess in the what Daniel was trying to capture, maybe it never be close to 2, right? But it will be, right, quite get there. So this is the ideal form, right? And we'll put a concept on this, all right? But of course, this is actually the easy part, right? Believe it or not. The hard part is to establish that yn does converge to 2. Because here, right, the thing is, if there is a limit, then this must be true. We never say anything about, right? Just because you can solve for something like this doesn't mean that this sequence must go there. That's a question of conversions, okay? And you study in drill analysis. All right, so to establish whether this really go there, I can tell you it does, right? But to prove beyond any doubt that this is the case is not for something for this class, okay? But so this is kind of, for me, is a fun example to show you what, right? To show you this kind of concept that that of 8.1 talks about, okay? So 8.1, what they look at is something like this. So 8.1, roughly speaking, gives you the one-step recursion. Like xn plus 1 is xn squared minus 2. Xn plus 1 is minus xn squared plus xn plus 2. Okay? Yeah, and like clearly, right, the limit, when I say it's not 2, I was thinking too quick, but just by the nature of it, right, it must keep on increasing, and it starts from square root of 2. I mean, just the whole nature of square root doesn't allow it to be -1, right? Yeah. Okay. So this is problem number 1, right? And this is problem number 5. So what is this, right? One step means, you know, the next step is given as a previous step, right? So the question, one of the question is find the fixed point. Okay, and so one of the question, right? There are other questions, but find the fixed point. So what does a fixed point mean? The fixed point means, right, that if you start there, you stay there. If you start there, you stay there, right? But that's exactly right. So okay, so let me say this, right? So xn plus 1 is equal to f of xn, right? It's the generic setup of 8.1. By the way, right, as I said, recurrence can be 2 steps, 3 steps behind, right? It doesn't have to be just 1 step. But if it's 1-step recurrence, like corresponding to first order differential equation, right? Or this is first order difference equation, then the fixed point, right, is defined to be the fixed point is a solution to f of x equals to x. Is that okay? That's exactly the analog of our equilibrium solution, where equilibrium solution is let's say x prime equals to f of x, right? f of x0 equal to 0, right? But of course, the difference is here we look at the change of x. So we look for the place where the change is 0. Here, right, is a natural progression. So that's why you look for the place where, you know, it mapped to the previous point. Of course, you know, like, right, with any progression scheme like this, you can always change it to a difference equation. There's just no point in doing that. For example, if you want to write as a difference equation, you can always do something like this. Right? So this language, right, says that from the previous point, you go to the next point. This language describes the displacement, right, from the previous point somehow, right? The displacement as the function of a previous point. You know, they're different point of view, but of course you see, right, if you put in this language, then exactly, right, the analog is find a place where displacement is equal to 0. So, right, that's exactly that. Okay. And if you pay attention, right, this exactly was looking for the fixed point of this. Is that okay? So, right, I was doing a fun example, but really that was looking for the fixed point of this relation. Okay. So the fixed point, right, are the points where, again, right, when you start there, you stay there. But just like equilibrium solution, right, in the you know, the differential equation, right, that they can have different nature, right? They can be sink, they can be source, they can be center, etc. Right? So same thing here, right? In a sense, right, what we're saying is, right, number 2 right here is the sink, right? I mean, the language doesn't go there as much, but because I say, right, the points go to this, right? I guess, I mean, depends on where you start, right? So here, right? So establishing the fixed point doesn't mean that it will converge to that fixed point or diverge away from that point or whatever the nature, right? That's another question we want to look at. But right, the first one is just to find a fixed point, okay? And so I guess it's easy, right? For example, number 1, you just solve for x squared minus 2 is equal to x. In number 5, you solve for minus x squared plus x plus 2 is equal to x. Is that okay? So that's the first thing you do. Find the fixed point. Okay. Then the next thing they want you to do is to find the cycles, right? Let me see here. So cycles, I'm not sure if it's like the circle in the differential equation setup, but for example, let me see here. What example do I want to look at? I think let's look at an example like this. I think this is true. Suppose that you got, right, xn plus 1 is minus xn cubed. Yeah. So the quadratic equation will have 2 fixed points. Yeah, exactly. Correct. By the nature of the equation. Yes. Mm-hmm. So this is the equation, right? Xn plus 1 is the recurrence relation. Now, first, let's find fixed points. So what's the fixed point, right? The fixed point satisfies minus x cubed is equal to x. So yeah, I think we'll already count. Hold on, I'm not sure. This is minus, right? Yeah. So x equals 1, 0, and minus 1. Okay. Now, but then, right, what the next one I want is like find cycle of period 2. Okay. So yeah, right. So fixed points are like this. So if you start there, you stay there. Find cycle of period 2. Right? What does it mean? So oh, hold on, Will. Yeah, sorry, right? It's this, sorry. So it's just 0. Yeah, 0, right? Yeah. No. But the reason why I was confused, right, is exactly, yeah, so only 0, right, is a fixed point. But minus 1 and 1 has an interesting point, right? What about minus 1 and 1 in this point? If you start out, right, with minus 1, then the next one will be 1, right? Clearly, trivially. But then the next one will be minus 1, right? And so on and so forth, right? And if you start with 1, then the next one will be minus 1. Right? No. So we don't look at, these are all real points. We don't look at complex points as fixed point here at all. Yeah, these are real value sequence, okay? Real value sequence. Same as real value solution, right? When you find the complex, right? There's no complex equilibrium solution in our system, right? Only real solution. So same thing here, right? Real fixed point only. Okay. But so looking back at this example, right? So it has a cycle of period 2. Okay. So that's also a stable behavior, right? In the long run. It's a stable behavior in the long run, not quite like fixed point, but a cycle of some period. All right. So the question is, how do we find this kind of cycle? Is it okay? So you understand what I mean by cycle of period 2 and maybe cycle of period 3, etc. The question is, how do we find these cycles? Right? So the answer, right, is this. Okay. Suppose that we have xn plus 1 is equal to f of x. Okay. You denote, right, f to the k of x as f of f of x k times. Okay. Then the k cycle, right, points are the fixed point of xn plus 1 is f to a k of xn. Of course, right, with the modulo taking away the points that may belong to lower cycle. Okay, so what I mean is this, right? Suppose that, say you look back into this equation, okay? because 0 is a fixed point, right? It will be a fixed point if you repeat it twice. But clearly, you don't want to count 0 as a fixed point of as a point of cycle or period 2. Is that okay? Because repeating 0 like this, right, doesn't mean that it's going to be a period 2. So what you do, right, is you find the composition of the function so many times, and you look for the fixed point of that composition. But then you want to pay attention to the points that have been already counted, right, before. So let's look at our example. Xn plus 1, right, is minus xn cubed. You want to find the cycle of period 2. So f of x here, right, is minus x cubed. So f repeat 2, right? This is not f squared, right? It's going to be x to the 9th. Is it okay? It's x to the 9th. Because it's going to be, right, minus of x cubed, minus of minus x cubed cubed. Yes? So definitely not a square, right? X to the 9th. And so the cycle of period 2, right, we look for, right, f squared of x is equal to x, or x to the 9th is equal to x. Right? So you got x to the 9th minus x is equal to 0, x times x to the 8th minus 1 is equal to 0, right? So x times x to the 4th minus 1, x to the 4th plus 1 is equal to 0, which clearly yield x equal to 0 and x equal to plus minus 1. Is it okay? But, right, 0, clearly, like I said, right, 0 is a fixed point for, right, so what you're looking at is xn plus 1 is x to xn to the 9th. Clearly, 0 is a fixed point for this one, right? 0 is a fixed point for this one. But, you know, your purpose is to count the point of period 2 for the original relation, which is this one. So you don't want to count 0 here, right? So the point of the period 2, right, the cycle of period 2 is plus minus 1. Any question here? So to recap, right, we're going to do more next time. We introduced two notions. We look at the generic system like this. Okay. Now the book will also talk about x0 given. Okay. The book will ask you to do something like this. Look for the orbit of x0. So meaning you start with x0 and then look at this and then look at this. Okay. And so you observe the behavior. There's nothing there that we want to look at, but maybe we can do some problem. Next one, you want to find a fixed point. Fixed point means to solve for f of x equals to x. Then you want to find the cycle of some period. That means you solve for f to the k, right? But of course, again, right, this is composition. And you have to be careful to remove points that belong to all the cycle. Okay, so keep these concepts in mind. We'll do more examples from the text next time and finish 8.2. All right, thank you. See you on Thursday, right? Last class. Yep, thank you. Thank you. Yeah, it's possible to get any kind of period, right? I'm not so sure. I'm not so sure what example we have that would get period of 3, but yeah, I mean, sure, actually here, right? I mean, it's something like this. It's quite easy. Actually, the easiest thing to do is do a cycle, right? I mean, like, you know, how to say this? Hold on, right? I mean, it becomes, of course, if you want to look for a non-trivial example, then it's hard. But if you just want to look for any cycle, of course, there's always the mod example. So let me see here. We are doing a thing in physics with the equation is cycle undoubled. What do you mean cycle undoubled? Hold on. Maybe let me say you can speak now. Oh, so the cycle will not be odd. That's what you're saying. Yeah, thank you. Yeah, so I mean, you're quoting an example, right? So wow, that's interesting. So the A must be something special, right? The A must be some special function that forces that. Yeah. So I mean, like, no, but A has to have some form, right? Not A increased. I mean, like, what is for function A there? Right. So, oh, A times xn. Oh, really? I see. So you got xn plus 1 is A, a constant, times xn, and times 1 minus xn like that. I see. Oh, I see. I think it's really right, because if you again, the key I think lies in studying this. So f of x, right, is this. F squared, if you compose a function, this function by itself, you observe something interesting, because 1 minus xn, right? And you can look at f cubed. Basically, I believe that the structure here is there's some structure here. You see what I mean? Because if you plug in the function composed with itself, I already see this, the structure repeats. So exactly when you study this, I think you somehow can show that the cube, right? The cube, or the odd cycle, does not have any solution. And that's the key to solve that, I think. That's the key to understanding that, I think, right? I haven't looked at it carefully. I'll play with it tonight if I have time. But I think that's exactly the thing, because you see, this guy and this guy, when you compose each other, it repeats itself. And that's why. Yeah, it's an interesting example. Yeah. So, right, again, I mean, like, I believe that you found this doubling of the period interesting, right? So I don't claim I have any intuition into this yet. But what I'm saying is, like, basically you claim, right? The claim is this, that only f raised to 2 to the k, x equal to x, has solution. That's what you claim, right? Now, again, I think, right, because again, this is notice it's really I don't know, there's a term for this, but if x is between 0 and 1, right, this is really a power, the pair of this, right? If you do one, you get the other. So naturally, it's really repeat itself with power of 2. But any other structure, you get an odd thing out, right? You get an odd thing out like this, the cube. And so I have to write down a few terms to observe the pattern. But what you can study, right, is to look at the patterns in between and convince yourself why, like there's no solution in between, right? But first, I think this is easy to write down because this is repeat so many fold, right? For example, I'm not so sure. Is this the case? F4 is F2, F2, right? And then F8 is F4, F4, right? I think this is true. I hope. Oh, all right, I might be writing down some really bad math here. But if this is the case, right? I don't know. This might be really bad math. But if this is true, then you kind of understand why the structure repeats itself, right? Because this is bad math because it's really not power, right? This is composition, but there's a chance it may be true. So guessing something like this and playing around with the structure is how you understand why this works that way, right? Yeah, I'll take a look at this, all right? I think it's not that hard of a structure to study. Yeah, I think, right. Does that remind me of, is it like a growth with ceiling? No. Yeah, this is really something that should really have a stable point, right? Yeah. No, but it's really not growth with ceiling because you really say that the next point is this. Remember, the difference is this. If you want the difference, then this is the case. You need a difference term. You need a difference term. If you just say something like this is a little bit different, right? Like you said. So I'm not sure the roughly part will dramatically change something there. You understand what I mean? Because right here, you talk about the difference, right? So even though, so this is growth with ceiling because, right, if it's above this, then it makes the difference negative, that kind of stuff. Here, right, if xn goes above 1, it's just going to make this guy negative itself, not the difference being negative. So yeah, all right, I'll play with it, and if I have something interesting, I'll send you an email. Also, there must be a particular a for you to have a doubling. So the change of the period, depends on a. Ah, interesting. But it's stable with a, right? As long as a is positive, it has one value. What do you mean by one value? Oh, so the period depends on a. I don't see that here. Oh, again, I think maybe it has to do with this solution. Like somehow a controls a number of solutions here as well in some way. Wow. Oh, you know what? Here's another thing you can play with, even though that may be a little bit hard. Is really, right, the book talks about this. I did not mention, but you really look at, right, the line of the graph, right, x, and you look at, right, f to k of x, right? Let's say something like this, right? So basically, if the number of intersection is exactly the number of points you have. So yeah, but basically, I think if you look at this function, right, and how basically, I think changing the a is changing the slope of this line if you want, because the a will never change when you compose the function. So basically, you can do x over a here, I think, right? So you might as well just take the a away and then you do divide by a here. So I think that has to do with like the number of intersection, right? As this function changes and this line change slope as a changes, right? You see, like for example, this graph, if a is negative, you only have this. If a is positive, you have that. So again, right, by studying the graph of this and x, that could be, or just a graph of this only without A, right? And then you just plot X by itself with different slope. That could be profitable, I think. Right, right, right. So I don't know, right? But what I'm saying is like if you want to understand why the periodic behavior behave that way, that could be one way to look around like this behavior. Yeah.